Okay, in this video I'm going to walk through the solutions to these differential equations. So we have to find the general solution to each of these differential equations. This first one has no y, so technically we've been learning a technique called separation of variables, which we would use for the bottom one. You can do that as well here if you'd like, just to be consistent. I'm going to move that dx over there. So now I've got dy equals x squared plus cosine of x dx. And then you introduce the anti-differentiation symbol. The antiderivative of 1 dy we just call y. On the right side, it would be x cubed over 3 plus sine of x plus c, which would represent any constant. The next one has the derivative in terms of the x and y coordinates. So we do need to use separation of variables here. The one above, you could have just kind of thought of it as taking the antiderivative of x squared plus cosine of x. You can't do that here until you've separated the variables and gotten the x's with the dx and the y's with the dy. So here you can kind of think of cross-multiplying. So we get this. We introduce our anti-differentiation symbol. I'm taking the antiderivative of y squared with respect to y. So that would be y cubed over 3. And then the right side, it's x to the 4th over 4. And then only one side really needs the plus c. So I'll put it on the right side. I'm going to multiply both sides by 3 so that I get y cubed is equal to 3, I guess I can call it 3/4 x to the 4th. Now you can write 3c here, but you could also just keep it as a c, okay, because that constant will just remain a constant until we plug in an initial condition, which we don't have. But at this point, we just got a cube root, and we have completed finding the general solution. All right, and then we've got this last one, and then we're going to do a particular solution. I don't know why I skipped to number 5. I don't know where number 4 went. Anyway, the thing to notice about this one is you've got on the right side x's and y's, but they're kind of tangled up there, right? The only way I could expect you to do this is if they are separable. Okay, so these are all called separable differential equations. Ones that aren't separable are beyond the scope of this course. So I can factor out an x to leave behind this 3 plus y. That's what you need to do first. Now you can actually separate the x and the from the y terms. Okay, so now you have to divide by 3 plus y and multiply by dx to make it look like this. Okay, just note this process alone, if you at least get here, I would give you, or the College Board as well, would give you some credit, okay? The separation of variables itself is a skill that gets rewarded with some points. But at this point, we take our antiderivatives, okay? The right side, remember, would just be x squared over 2 plus c, just undoing the power rule. The left side, you have 1 over a linear term, 3 plus y is just, would graph a line. That's when it's appropriate to use ln. So we're going to use the ln symbol. Now, we've talked about this in class for those in my class. The natural log of the absolute value of y plus 3. So you need absolute values there. We want to solve for y, so we need to turn this equation into its exponential form. So the base of ln is e. So I'm going to say e to the whole other side. E to the this is equal to that. So I get the absolute value of y plus 3 is equal to e to the x squared over 2 plus c. Note that's up in the exponent. Okay. note that this here can be re-expressed through properties of exponents as e to the x squared times e to the c. And that e to the c, it's typical and conventional to replace that with another letter because e is a number, c is just a constant. So this would be some other number. And whether you find what c is and raise e to that number, or just, find the constant later when you plug in an initial condition, it's typical to just call that something else. So I'm going to call that an a. So now I get absolute value of y plus 3 is equal to, I'm going to glue the a in front, a e to the, let's zoom in here, x squared divided by 2. And then same thing, absolute value of something equals, absolute value of y plus 3 equals a e to the x squared divided by 2. I've probably pointed this out before, but just remember, the absolute value of x equals 2 tells us that x equals plus or minus 2. So you could say y plus 3 is equal to plus or minus a e to the x squared over 2. But again, this a is to be determined. It could be positive or negative. It can kind of absorb the plus or minus, so it's not really necessary to do that if you don't want to. We minus 3 and we're done. So y equals a e to the x squared divided by 2 minus 3. And we're done. And let's do kind of another one in a similar fashion, but find the particular solution. Oh, I have an initial condition now, so I can find the particular solution, which basically means I'm going to solve for the c or the a, depending on what ends up showing up. You should notice the structure of this is exactly like the other one, right? Except I've got a 5 instead of a 3, so I hope I'm dropping you some hints here. In any case, we factor out an x, 5 plus y. We separate the variables, so I have dy over 5 plus y is equal to x dx. I anti-differentiate. Let's go up here. And then I get, so the natural log of, I'm going to write it as y plus 5 just because I want to. And then this is x squared over 2 plus c. And of course, at this point, I hope you've figured out we're turning it into exponential form. E to the, I guess I usually started with a y. Y plus 5 is equal to e to the x squared over 2. Let's just, maybe not, maybe I'll break it down so I don't do too much at once. So again, notice that this is equal to e to the x squared over 2 times e to the c. I'm going to replace that with just an a. So I have what? I guess I should have put that there. Absolute value of y plus 5. Absolute value of y plus 5 is equal to a e to the x squared divided by 2. Again, plus or minus a, that can kind of absorb the plus or minus. And then I got y equals a e to the x squared over 2 minus a 5. So I waited to the end to plug in my initial condition, mainly because I have experience with this, and I just learned that it's going to be, I think, simplest to do it here. You could have plugged in at any time, you could have plugged in the 0.06, like here, for example, and you'll end up in the same spot. But I think it's easier to wait to the end in this particular case. So I know that y, f of 0 or y of 0 is equal to 6. So when I plug in 0 for x, I need to get out a 6 for y. So 6 is equal to a e to the 0 squared over 2, which is just e to the 0 minus 5. E to the 0 is 1. 6 equals a minus 5. Add 5 to both sides. A is equal to 11. And so my particular solution would be y equals 11e to the x squared over 2 minus 5. There are four differential equations, one with a particular solution, that you should be prepared to do if you are taking my midterm.